pleasure to welcome Schaubach, one of our own. The song being inducted as one of alumni, and it's great to have him here. So he'll be talking to us about the broad theme of spectrum sharing, a lot of you. So Schaubach is the CTO of the officer at Generative Wireless, where he leads R&D, technology strategy, and product development. He pioneered the development of generative SAS, ESC, AFC technologies, and the development of the 2.5 gigahertz CBRS spectrum sharing system. We have over 30 years of experience working beyond this year in senior technical management roles, in active in spectrum development, management, and policy. All to the technical side of policy. Throughout his career, Kurt received ES department back in 1990, and his MS also known as so again, the broad theme of the talk is spectrum sharing.
Thank you. Let me do a sound check real quick. Everyone can hear me okay? Are we good on Zoom? Terrific. Well, good afternoon. Thank you so much for the opportunity to be here today. I mean, this is a great honor for me, and I very much appreciate. Thank you, Scott, for the the kind offer to be inducted into the Alumni Hall of Fame, I guess you could say. Anyway, again, my name is Kurt Schaubach. It's a pleasure to be here. Over the next 45 minutes or so, I'm going to try to cover two topics related to spectrum sharing. Why is it important, and what is it? And if I'm successful, you all will have lots of questions. So I'm going to try to get through this in about 45 minutes or so, and of course, want to just leave as much ample time as possible for you all to engage and ask questions. So, great. Let's see. Is it?
Up arrow to the right.
There we go. I'll just use the keyboard the old-fashioned way. So, as you heard in the introduction, I am a proud Hokie and graduate of Virginia Tech, both as an undergrad and grad student. Maybe somewhere in the deep, dark recesses of Whittemore Hall, like if you go all the way down one of the stairwells, you might still see the class of 1990 class photo. There were probably quite a few, much smaller class way back in 1990 compared to what, enrollment is today. But just a little bit more background on me personally. I am born and raised in a town called Oakland, New Jersey, up near New York City area. As a high school student, was super excited to discover Blacksburg and escape from the Northeast to the South. In high school, I probably like many of you, thoroughly enjoyed math and science. Those were my two favorite subjects, and I was also into sort of stereos. I was what you might call like an audiophile. That was actually a thing back in the 1980s, not so much now. But what fascinated me when I was, sort of a teenager before heading off to college was how sound waves propagate. So obviously there's a lot of relevance to that in terms of wave theory and how that applies to, a career that I've since pursued over the last 30 years. I'm married. I have 4 children. My oldest child is a recent college graduate. I have 2 children in college. High school, my wife and high school sophomore are here actually with us today. So far, I'm 0 for 3 in terms of producing an engineer in the family, and I think I'm going to be 0 for 4. So, but anyway, that's quite all right. They are doing well and pursuing a lot of their their interests in academic pursuits. I actually, as a graduate student, I was working on things related to propagation modeling. As I said, I had a keen interest in things like wave dynamics and electromagnetics as an undergraduate. And while I was working with some with the group known then as MPRG, which is now wireless at BT, we were doing things related to channel sounding, doing propagation measurements, and actually trying to generate models around how propagation worked in our physical environment. After grad school, I started working at a company called Southwestern Bell, which you probably now know as AT&T Wireless. When I started my career, this was the latest technology in wireless, and this. So yes, gives you a sense of just how much technology has changed. I dare any of you to figure out how to text on this, unless watch a video. I really fortunate to have worked with a lot of different technologies, literally everything from 2G technology now up to 5G, and a bunch of other things along the way. But I think what's really interesting is that while technology has changed, and clearly it has evolved, a lot of the problems that we identified almost 30 years ago now are very similar to the challenges that we face today in the wireless industry. So again, for example, as a grad student, we were working on channel modeling and RF propagation modeling. That is still a sort of a topic that we have not quite overcome or mastered, when it comes to wireless. And believe it or not, that group there that you see sort of in the center picture, that's when I was with Southwestern Bell. The very first program I worked on when I was graduating, a new graduate working on, in the professional world, was related to spectrum sharing. That is actually all that equipment there sort of represents a giant sensor that we developed to actually demonstrate that spectrum sharing would be a viable technology. So here we are again 30 years later, and we're still kind of working on perfecting these sorts of technologies. So today I work at a company called Federated Wireless. It was really interesting to come back to the building here because actually some of the founding members of Federated Wireless team who helped develop the early IP for our company were Virginia Tech faculty. Jeff Reed, Charles Clancy, who was with the faculty at the time. And this was kind of this building was our very first office. A couple of us worked out of this building as we were kind of getting the business going in the 2014, 2015 timeframe. Today, we're 65 people. We're now headquartered down in National Landing, close to where the other sort of new innovation campus is located. We have an office up in Boston. Probably about half of the company are technical in nature, engineers, software developers. We are very much a software and software automation company. And a lot of the work that they do is around, developing spectrum sharing technologies in the cloud. I'd say of our technical team, probably a good half of them have advanced degrees, computer science and electrical engineering, applied math. We do a lot with data and data analytics, even things like AI and ML now. So I very much applaud you all for your pursuits, in terms of, your efforts to get a graduate degree. It is very relevant once you get out into industry to have, that additional sort of education and experience, the work that you do as part of your master's or PhD thesis. Those are, really form a great foundation for the what will hopefully be a very enriching career for you to come as well. Okay, so onto the topic at hand, and I'm going to cheat. I'm actually going to answer the first question, why is spectrum sharing so important, with just one slide. Everything else will be a little bit more of a discussion around what are we doing currently with spectrum sharing, where is it going. But you'll see on the left, what I'm calling Exhibit A is mobile data traffic growth, where we're at today and where it's projected to go here in the future. So this probably comes as no surprise to you all, but today we're at about, globally, we're probably at about 130 exabytes of mobile data traffic per month. In about 6 years, we will be 3 times that. So data traffic is growing at a roughly 20% year over year kind of rate. And, you can see the curve is only sort of increasing with more positive slope, right? It's going even sort of asymptotic there. So tremendous growth in data traffic. And we have this other challenge here on the right. This is actually a frequency allocation chart that the NTIA maintains. This is what our spectrum landscape looks like in terms of, if you look from DC to daylight, more or less, how spectrum is currently allocated or licensed here in the US. And it is complicated. You can see that there are, it's not like this is a simple chart with just, a few allocations. It is allocated for all sorts of uses, civilian, commercial, defense related, the US military, for all sorts of different uses, radars, other radio location services, satellite, terrestrial wireless, fixed wireless, more or less, you name it. Everything that you can imagine has to have some sort of, today, some sort of application associated with it. The challenge is that, sort of the added challenge is about 60% of all the allocations at 6 gigahertz or below today are allocated for some sort of federal use. So when you think about the commercial wireless industry that has to deal with this sort of, astronomical growth of data traffic, they are hamstrung by the fact that a lot of the spectrum that would be most immediately usable for mobile wireless services is in fact dedicated for other purposes, federal, other non-federal uses that have nothing to do with what we know as commercial wireless. So what do we do about this, right? We sort of, as engineers, and the oath that I just took, talked a lot about how do we make best use of our precious resources. We have to figure out how to use the spectrum more efficiently, right? So we really only have 3 tools available to us. One is to improve the spectral efficiency of the technologies that we operate, right? Today, 5G obviously more efficient than 4G and so on. But that's only going to solve part of the problem that you see on the left. We can only just get so much increase in spectral efficiency with each new technology. And it takes almost a decade to go from concept to commercial reality every time we go through a new sort of generation of 4G, 5G, and so on. The other thing that we can do is sort of densify networks, right? We can not only increase the bits per hertz efficiency, but we can improve the bits per hertz per unit area efficiency of networks. But to do that, you're talking about huge capital investments and other complexities, practical realities that you can only deploy so many, small cells, so many cell sites in a certain geography. So clearly we have to find a way to manufacture more spectrum. And the way to do that is through spectrum sharing, right? Because we all know we, in fact, can't manufacture more spectrum, but if we use it more efficiently and we find ways to multiplex more users into a certain allocation of spectrum, we can, get obvious efficiencies from that. Those are really sort of the 3 dimensions of what we can work with today in the wireless industry, and that's why spectrum sharing is really so vital to our wireless future, is because we just simply have to find ways to increase supply as well as, improve network capacity. So how does this happen? One key thing that is required, sort of an entry criteria for anything related to policy, spectrum policy here in the US and frankly abroad, is related to building trusted partnerships. A lot of my job is to spend time working with individuals, explaining technology to non-practitioners. And in fact, I've had sort of the unique, honor of going to the White House, going to the Pentagon, to meet with folks from the DoD, from Office of Science and Technology Policy, the Federal Communications Commission, which is the primary entity that regulates commercial spectrum, NTIA, which is part of the Department of Commerce that does federal spectrums. We have these 2 entities that kind of handle different aspects of spectrum regulation, and all sorts of different, government agencies, from branches of the Department of Defense to the Defense and Information Services Administration. So this just gives you a sense that when you're talking about how to create a model to share spectrum, that in some cases the spectrum might be used for national security, might be used for protection of life, like in public safety, it's vital that we are able to build trust and can not only convince them that the technology works, but that we can be, for example, we as Federated can be good stewards of of how to implement and operate technology. So a lot of what I'm going to talk about in terms of how do we effectuate and sort of realize spectrum sharing commercially is around how we build in things like reliability and high availability into the platforms and capabilities that we develop. So spectrum sharing, actually, as you think about it, there are a lot of opportunities. I mean, clearly that NTIA chart that you saw, you might think, well, everything's really a candidate, but there's sort of this process that we go through as an industry to identify specific bands that become candidate bands for us to study jointly between the incumbent users, those who are sort of currently located in the spectrum bands, and the sort of the industry at large who's interested in gaining access to the bands for sharing purposes. We convene these groups that are sort of moderated through the FCC or NTIA to study bands and identify ways in which we can create perhaps a sharing paradigm. In fact, today, those two blocks in green, what we today know as the CBRS band and the 6 gigahertz band, I'm going to talk a little bit more about. Those are bands that are actually already very either fully commercialized in the case of CBRS, or in the case of 6 gigahertz, really on the cusp of commercialization in terms of actually demonstrating spectrum sharing and kind of the commercial reality. All these other bands, from things that are sort of down in low band all the way up into the millimeter wave, are bands that we're currently working on to sort of increase that pipeline that I was referring to, related to new bands that we can do shared access with. Some of these bands are used by the DoD today or used by the commercial industry. You all have different elements related to the incumbent uses that we have to account for and study in order to come up with a sharing paradigm. So as I said, I'm going to talk a little bit more about CBRS and 6 gigahertz, try to compare and contrast them a little bit, give you a sense of how those kind of operate today commercially, and also maybe give you some perspective on where we might go next in terms of applying spectrum sharing technology. So if you think about what we do in terms of spectrum sharing, it all sort of comes down to this concept of an engine. I'll call it a dynamic spectrum management system that is sort of at the heart or the core of how we enable spectrum sharing. And today what we do is we actually develop these technologies in the cloud. And regardless of the band that we're talking about, whether it's the CBRS band that I'll talk more on, or 6 gigahertz, it has some elements of this kind of basic architecture. And essentially it starts with a sort of a computation and authorization check engine. So computation would do things like interference modeling, propagation modeling. We provide the basis to understand where and how spectrum sharing could be applied, how new uses could be integrated into a band while providing protection to existing incumbent uses. Authorization check is sort of the rules engine, because there's a lot of things that we have to think about in terms of assigning spectrum near the Canadian border, the Mexican border, or when we have coastal operations versus operations inland where we might have different incumbents that we have to protect. So we have to create sort of a rules engine that informs or advises the process of assigning spectrum. And then there's sort of like around this computation engine or an authorization check, there's a number of capabilities related to different databases that feed into the propagation modeling, clutter and terrain, license databases to the extent that the services or technologies that we're sharing spectrum with are entities that are licensed and are recorded in some database. We need to interface with those systems. Sometimes we have to peer with other systems to share information. There's more than one platform helping to enable or effectuate spectrum sharing. We have to do that peer-to-peer communication, coordinate with them. And then also, receiving other inputs, for example, sensor inputs that might be necessary to detect and avoid incumbents or protect incumbents that are itinerant, that move around, that are not always transmitting, that don't appear in a licensed database, a licensee database. We may need to incorporate some sensing technology in order for us to, properly account for them in the spectrum sharing model. Okay, so as I said, two bands we're going to talk about. CBRS band. It sounds like maybe some or a lot of you are very familiar with CBRS. I'm excited to hear that. That's actually kind of a topic that you all cover in your maybe some of your graduate work. So I'll maybe go through this a little bit quickly. In 2012, the FCC first designated 150 megahertz of spectrum in the 3.5 gigahertz band, sort of beachfront property in the spectrum world around commercial wireless, as a candidate for sharing with the commercial sector. Something called the Spectrum Access System, a variant or version of that DSMS that I just showed on the last slide was identified as kind of a core system that would manage the band. Also a sensor technology that I'll talk more about that is used to detect federal incumbents, because the predominant two incumbents in this band are radars, radio location systems, that are operated on aircraft carriers or large deck amphibious vehicles that are used by the US Marine Corps, as well as some fixed services, so fixed satellite earth stations, receives earth stations that we have to provide protection to. So sensors were a necessary component to assure protection of those radars. The band was designated as technology neutral, meaning that it's not a specific technology or family of technologies that can operate. Any technology that can comply with the need to communicate with the spectrum access system can take advantage of this broad swath of spectrum. But what was key about this when we were actually getting started back in the 2015 timeframe is that in the US, the 3.5 gigahertz band is used heavily by radars, by the US DoD, Navy, and Marines. Globally, that band is actually a 3GPP band, meaning that it is a band that was already commercially designated for commercial wireless services. And we were able to tap into that sort of massive ecosystem as we were helping to get the CBRS band kind of launched and commercialized here in the US. Okay, so the model that was set up is this 3-tier model. You've got incumbents, and then you've got these 2 tiers of shared access, priority access licenses, general authorized access. The key point here is that this model provides for a great deal of flexibility. You can have a tier of access which provides more surety or confidence for users in terms of their ability to access spectrum and reliably utilize it, as well as a tier of access which is very opportunistic. And what I'll do is I'll relate that to specific use cases that we are now seeing evolve commercially. Because of this 2-tier model, we're actually seeing very broad adoption of CBRS across a whole bunch of different industries. And that's, I think, because of this sort of very flexible framework that was established. Basic concepts of how this works. So relate this back to that DSMS, sort of functional diagram that I showed. There are incumbents, as I mentioned, Navy radars, a sensor network that is used to detect and inform a cloud platform, what we call the Spectrum Access System, to manage spectrum. Devices, now when we call a device, what we're really talking about is a small cell base station, an E node B or G node B in 3GPP parlance, which connects to the Spectrum Access System through an API and gets a spectrum assignment. So you can think of this as almost like DNS for spectrum. It's really that simple where, the device communicates through a protocol, gets a spectrum assignment, and then periodically checks back in, performs what we call a heartbeat function, so that we know that the system is operating closed loop. And this is really important because if we detect the presence of an incumbent, suddenly a Navy radar appears that wasn't transmitting before, wasn't located near the coast before, we need to be able to communicate with those devices and have confidence that whatever information that we're sending to those devices about needing to change or reorient their spectrum assignments will actually be carried out. And that's why this sort of closed loop operation is very important. Everything that we do in CBRS is based on aggregate interference protections, meaning that You have to count for all of the devices in the ecosystem. You have to maintain databases around where those devices are located. Every device, every small cell needs to have the capability to geolocate and report its coordinates as part of the process of registering and authenticating with our platform. So it's a key sort of capability or requirement in order to make spectrum sharing work effectively in the CBRS band. So in some ways, there's real sort of elegance in the simplicity of what we do in terms of how we manage devices. We effectively do three things. We figure out how much bandwidth to allocate per user based on what the environment looks like, who is currently using the band, what we have to do to provide protection to incumbents. So think, for example, we might identify that we can allocate 30 megahertz to a user. We then determine what channels to assign to that user, so what specific frequencies that they operate in over the 150 megahertz of the CBRS band. And then we determine what is the transmit power that they can operate at. Those three components are really, the core of what we do with spectrum sharing. I mentioned the environmental sensing capability, this need to be able to detect and avoid incumbents. This was in the R&D work that we did, the product development, this was a very major component of the work that we had to do and coordinate with the Department of Defense. As you can imagine that us being able to listen to a very specific radar transmission signal or being able to geolocate where a aircraft carrier might be a little bit of a concern to the, to the US Navy, right? That could create a real sort of operational security threat for them. So we had to come up with a lot of really clever solutions to be able to sufficiently detect where the radars are operating without actually divulging any information that might create an operational security risk for them. That's an example of one of the sensors that we use as part of our sensor network. There's about 250 of these that are installed along the Atlantic, Pacific, and Gulf Coast. Our employee who gets to visit these sites, most of which are coastal, like at the beach or a nice hotel, I'm very jealous of him. He gets to, gets to sort of see, beachfront property all the time. So, but anyway, this is a big element of what we do to, to operate and share the CBRS band. This box, which is the sensor and the antenna, is part of it, power, and actually the sensor is up there. This is our power and backhaul and other capabilities to interconnect the sensors with our SaaS platform. A lot of really interesting technology that's built into that in terms of what we do with signal processing, how we detect radar signatures, how we mitigate other interference that we might see in the band. Because you can imagine, while there are live users in the band that are co-located in the same spectrum as the Navy radars, we have to have the ability to eliminate the potential for those CBRS shared access users to create interference to the sensors that would otherwise degrade their performance or limit their ability to, to detect a Navy radar, which may be many, many miles out at sea. A lot of things that we had to do around protecting for very harsh conditions that are at coastal areas, around humidity and sea salt and all sorts of other things. So very sort of interesting kind of engineering exercise that had to go into that in addition to the work that we had to do to build our cloud platform. The way the protection of these federal incumbents work in the CBRS band is around notionally creating what we call these dynamic protection areas that we sense for a Navy radar. If we identify that something is in one of these locations, that's when sort of a action needs to be taken by the SAS to reassign users and provide protection to that Navy radar. And this is where really the power of the cloud comes into play, because what I'm sort of depicting here is kind of a simulation of what we have to be able to handle in terms of computational capacity, complexity, in real time to provide incumbent protection. So all of those little dots are intended to signify different small cells that might be operating in the band, that we have to consider their potential impact to a protection point somewhere within this dynamic protection area. And in real time, literally within seconds, be able to handle that computation to say, will devices, create an interference level that is harmful to something operating in this region, a radar operating in that region? If so, then we need to, through this software protocol, be able to advise that device that they need to relocate to another frequency. And all that has to happen within the matter of computations as well as the actual moving of those devices to other bands within 5 minutes. So that's why, I think that technology that I was referring to about spectrum sharing back in the 1990s was interesting, but really was sort of not commercially viable because we didn't have the power of the cloud back then. We didn't have the ability to handle the massive computations that are necessary to really do spectrum sharing at scale. One thing that's really important in terms of not only the development of the technology is the creation of an ecosystem around spectrum sharing. And there are 2 sort of main ways that you do that. One is to create a standards body that defines specific standards around interoperability and technical standards around performance, and an industry alliances that kind of help promote the concepts and the commercialization of technology. And one of my jobs while I was at Federated Wireless was to really help get these 2 different organizations, started, do a lot of the standards and standardization work. Folks from my team did that. We at Federated helped create the ONGO Alliance. Now it's about 200 some odd company members, all that sort of align and work together to promote the adoption of shared spectrum and the CBRS band generally, but to create kind of commercial traction around this. It's very important that you have to do that because without some level of interoperability, without sort of standards, it's very difficult for companies to build products and do it at scale. So, as I was referring to, one of the things that we do is we create these sort of functional architectures. We define the interfaces and the protocols, the communication protocols that are used to communicate between platforms with devices. And we actually run interoperability testing. I think actually some of that's going on upstairs, even with the 5G O-RAN lab and the OTIC certification that Virginia Tech has. Hopefully you all can through that kind of appreciate the importance of the standards and interoperability, because you want, as a vendor of a device, a creator and inventor of a device, you want to know that if you have built your software protocol to communicate with the federated SAS compliant with the standards, that it will just work, that it doesn't require constant engineering and technical support and other things in order to get it to operate. So that is a key aspect of what we've done through the standards efforts. I talked about these 2 tiers of sharing: the priority access licenses, the general authorized access licenses. There's also different categories of devices: small cells that operate in the CBRS band, higher power ones that operate outdoors, lower power ones that operate predominantly indoors. That flexibility, again, helps create a very vibrant ecosystem, lots of different use cases. So this is, I think, this is really like the money slide. This is the most exciting part of what we've been able to do since we commercialized the band. Really drive very broad adoption across a number of different industry segments. So today, CBRS is used by large mobile network operators to help add capacity to their networks to address that commercial, traffic growth chart that I showed early in the presentation. Cable companies, so you may be aware that companies like Charter and Comcast are now becoming wireless operators. They're transitioning from their old business of linear video to the home to provide broadband and provide mobile broadband. And as part of that, they are using CBRS as a way to build that mobility, that wireless mobility network using their cable plant and cable infrastructure. Broadband wireless access, this is very important in rural communities. The notion that if there is no fiber or coax or fixed line service to the home, you can use wireless technology. In fact, a lot of this now is with 5G. Use wireless technology as a way to provide alternative broadband connectivity to the home. So very powerful use case for CBRS. And the other two areas are private networks and neutral host networks. And I'll talk a little bit more about those in a moment. Those are, I think, probably the two most interesting and exciting growth areas in terms of CBRS. This is just a quick profile of some of the customers that we work with on a day-to-day basis. So we as Federated have about 450 customers. They range from very large service providers, cable operators, all the way down to literally we have customers who serve maybe 10 homes with a fixed wireless access solution. So, very broad range of sort of customers that we're able to support, enable access to CBRS so that they can deliver on their business plans, deliver what they're, maybe solve a really difficult problem in their community to, connect the unconnected. So I think one of the most interesting aspects of CBRS is how we've been able to sort of democratize spectrum access and access to 4G and 5G technology. So until CBRS came along, the only way that you would have the ability to operate a 3GPP compliant 4G wireless network is if you had licensed spectrum and a few $1 billion and relationships with very large equipment suppliers like a Nokia or an Ericsson. Through the CBRS model, we've been able to really democratize spectrum access and access to 4G and 5G by creating, as I said earlier, through things like the Ongo Alliance, this massive ecosystem. What this helps stress is a real prevalent challenge in wireless today, which is in-building wireless coverage. All of you know that most of your wireless use originates in the home, inside buildings, dormitory or apartment. It's not sort of the conventional outdoor macro network-led wireless any longer. We really need to find ways to bring coverage, bring wireless capability indoors, because literally only 2% of the buildings today have some sort of solution that is used like distributed antennas or small cell technology that is used to provide coverage. So there's huge challenges in terms of in-building coverage. And along with that, there are needs that enterprises have to provide greater levels of connectivity for their their enterprise applications. Things like the Internet of Things that will handle things like building automation, robotics, other capabilities inside buildings, offices, warehouses. They need 4G and 5G technology in order to thrive. Wi-Fi has been tremendously successful in providing basic connectivity inside buildings, but as you all know, can't really rely on it when you are concerned about security. You need very low latency and very high bandwidth on a consistent basis. You need a more robust technology solution. That's what CBRS is able to enable. And importantly, it also brings about this thing that we call in the industry neutral host, which is notionally how carriers can bring their wireless signals indoors. So how a Verizon or an AT&T or a T-Mobile can bring their service indoors and serve their subscribers through small cells that are deployed in the CBRS band. And I'll talk about a little bit more about how that works architecturally. So all of this private networking is possible because of some real key changes that have happened recently in the device. Two really important, sort of evolutions are eSIM technology. So now your, sort of legacy devices and wireless had a single physical subscriber identity module, physical SIM, that had the credentials that were used to allow you to authenticate and connect to a network. Today, now you can set up multiple profiles inside of the device through eSIM technology. And that allows you to, bring your own wireless device and have private network connectivity, say in your enterprise, by the enterprise being able to create an eSIM profile that allows you to connect to a CBRS network and authenticate against the enterprise, IT domain. The other thing that has been a recent development is something called dual SIM, dual standby. What that allows the device to do is effectively become a control point for connectivity. It can identify whether it should switch between the public network, the private network based on a rule set that you set up in the device, sort of a rules around what signal level, what, geolocation parameters that will allow you to identify which network you would optimally connect to. If you go through, like sort of recent releases of iOS, you'll see a whole write-up from Apple on sort of all of the functionality that they're adding to your iOS, same for Android, around dual SIM, dual standby, eSIM, to enable private networks and things like neutral host. And this is really, I think, in many respects, a very big game changer for the industry. This is going to really radically change the way we think about wireless connectivity. The way neutral host works in the old world, you would have to roam between networks. You would have to effectively disconnect from one network, connect to another network. These networks were sort of their own separate islands of capability and coverage, very expensive and inefficient. Now with things like neutral host, what happens is you deploy an eNode B inside a building, and through a gateway, we are able to connect back to multiple service provider networks. And through the eNode B, advertise each of those networks and allow you to connect with your SIM credentials to the eNode B, sort of route that traffic back to each of the carriers. So private network, as well as the ability, for example, to connect to the Verizon network, all within the same building, all using the same small cell, managed through different IDs that the small cell will transmit, and then this neutral host concept to manage and route traffic and allow users to authenticate back. So this is how we will get to having really robust in-building coverage through a very economical sort of platform and solution. So a little bit more on some private wireless use cases. These are actual deployments that we've done with private wireless. Everything from adding a connectivity to a smart pier with Cal Poly to, I'm going to talk a lot about this smart logistics work that we've done. We're working with Travis Air Force Base out in California to bring a connectivity solution to large aircraft where they're managing the equipment and supplies that are going on and off the planes for logistics. Smart venues, we've done work with AWS. They have this big event that they do every year out in Las Vegas called reInvent, and we provide the connectivity to allow them to do scanning to badges and facial recognition, provide security and communication for individuals who are, sort of part of the operations staff associated with running an event. Other smart campus capabilities, in fact, again with Cal Poly, we've provided the ability to offer E911 services in areas where there's very limited or no mobile network operator coverage, so providing greater security and safety on the campus. Smart City, JBG Smith, which is actually, some of you may know, is kind of the redeveloper of the whole National Landing where the Innovation Campus is located. AWS is located with their new HQ2. They're doing all sorts of smart signage, smart buildings, and we're helping to enable that through CBRS. Really interesting program that we did for robotics. Actually, this was retrofitting like an old big green John Deere tractor with a capability where the tractor could be completely controlled over a 5G network. So really interesting developments around bringing more efficiency to to things like agriculture, which are really today have been very devoid of any sort of advanced technology. So really interesting. I'll talk about a little bit more about what we're doing in Albany, Georgia, actually. This is with the US Marine Corps. We have built out a complete 5G platform using private wireless, again, private, secure, dedicated network for the Marine Corps to use, independent of the mobile network operators. They can operate this network completely private way, covering a whole bunch of warehouses to provide greater, productivity, ability to manage, their warehouse logistics and all sorts of things. So actually in this warehouse, we're using both CBRS as well as millimeter wave spectrum that's shared. got, I mean, you can see here just some of the performance and capabilities with 5G. So 5G NR on CBRS using 40 megahertz and 2x2 MIMO, 300 megabits per second. So that's screaming fast. Really, really incredible broadband capabilities. And what they are using it for is to modernize their entire operation. Literally before, they had people going around with clipboards and paper and pencil to keep track of really, valuable and important assets. Now they have barcode scanners, they have robotics that will, do shelf counts, based on RFID tagging. They have robotic arms to unpack things as they come into the warehouse or pack pallets before they ship out. And you can see sort of along here at the bottom some of the metrics that we have been able to demonstrate through private networking and use of CBRS. Lower labor costs, better velocity of goods moving through the warehouses, much greater accuracy in terms of knowing what's actually, in inventory. So this is really important, maybe even the recent experience that we've seen, in the Ukraine, logistics matter quite a lot for, the war fighter, for, on military operations. So it's very important that we have, efficient logistics. I think I covered a lot of this already. I'm going to just keep sort of cruising, but that was CBRS, some of the use cases around CBRS. I'm going to just briefly, with the last bit of time remaining, talk about the 6 gigahertz band. So CBRS has now been commercial for a couple of years. We've been operating in that band with a certified and commercial platform. As I said, hundreds of customers. The 6 gigahertz band is literally now on the cusp of us, bringing to, commercial availability. What's different about this band is a lot more spectrum. It's 1200 megahertz of spectrum, so like almost 10 times the size of the CBRS band. It's an enormous amount of spectrum that's going to be shared and made available for new commercial uses. And what is interesting is that this is a little bit more technology specific, because in order to use this band and gain shared access, what the FCC has designated as part of the rules is that only unlicensed devices, so think like Wi-Fi, can utilize this band. So this band, for example, is not a 4G or 5G band because of the way that we are actually sharing and providing incumbent protection. So it's a little unique and different in that sense. But again, what is also, I think, unique is, in the CBRS band, we're sharing with something like 30 different ships that have that radar that I was talking about, that we sense and detect and avoid, and maybe a dozen or so satellite Earth stations. Here we're dealing with hundreds of thousands of fixed microwave links. So these are point-to-point links that, I'm sure you've seen these. They have sort of these parabolic dishes that are used to provide backhaul or connectivity. A lot of cases, these are used by the wireless carriers to provide backhaul to cell sites. So it's like one of the very, very common uses here. But you can see, this is a map that is depicting all of the uses of these fixed services across the U.S. And you can also maybe envision a lot of white space there where there's an opportunity for us to, effectively share. In this band, the FCC has designated a couple different devices and device categories, sort of similar to CBRS. So we're talking about different power levels. But in this case, the highest power level is 36 dBm, so quite a bit lower than what we can do in CBRS. This is designated a little bit more for things like indoor enterprise applications versus, those bigger outdoor, sort of uses, carrier uses, like I was referring to earlier. And what is also unique is that in this case, the FCC is mandating that a spectrum sharing platform is known as the Automated Frequency Coordinator, in the case of the 6 gigahertz band, be used only for a certain device category. So certain devices are allowed to operate without any sort of closed loop operation, don't need to check into a database, because they're operating at such a low power level, they will not cause interference to the incumbent uses. But the single category of what's called standard power, really the high power uses, those devices, which could be, for example, maybe used outdoors to provide some local area coverage, or in factories, or applications where more power is needed. Those are the ones that actually have to connect and coordinate with the AFC. And what we do in terms of how we effectuate sharing and compute interference potential is a little bit different. The specific sort of scenario that we're looking at is these point-to-point links. They're often installed or designed to operate well above the local area clutter. Many of the shared access uses are down in the clutter, so we can sort of orthogonalize those uses and be able to present a solution for sharing where even in the same geographic area, we can allow these shared access uses to occur. Same basic concept around how the AFC operates. Again, going back to that ESMS concept, computation engine, a lot of databases, licensee databases that we access. Know where those point-to-point links are. Protocol, software-defined interface that is used to communicate with like the Wi-Fi access points to identify what spectrum is available for use. So architecturally very similar, but what's different is this is not a closed loop system. You just sort of transmit a list of channels that are available for the device to use, and then it picks from among those which one it wants to use, rather than having to constantly coordinate its bandwidth, power, and specific frequencies of operation. Some interesting things that we've had to sort of deal with in the 6 gigahertz band is how to deal with the geolocation of devices that are indoors. We've created some concepts around how to deal with the uncertainty of the device location, some of the computations that we do. So we create these 3D models around, the known device location, and as you would expect, a lot of fairly sophisticated propagation modeling and other things that go into computing where and how spectrum is available and how many channels or what power level a device could operate at. So we're going to create these heat maps of channel availability and power availability, which then translate into sort of these rasters or dashboards, if you will, that are transmitted sort of over that protocol or interface to a Wi-Fi access point to identify what frequencies it can operate on. So it gets this channel list. Some channels may be able to operate at full power, some may be at maybe marginal power levels. It then picks and chooses how it wants to, what channels or what range of frequencies it wants to operate on. So that's a little bit about 6 gigahertz. So last slide, and then questions. Hopefully we still have some time for questions. So we've done a lot already in terms of commercializing shared spectrum, demonstrating the commercial viability, creating new use cases. There's still quite a lot we can do in terms of R&D and future research interests that we have. One area that we're doing a lot of work in is helping folks like the FCC and NTIA, who maintain these databases and use tools to manage and coordinate spectrum, helping them modernize the systems they use so that they have more accurate records around where and how spectrum is actually being used. Today, that's a little bit of a challenge to kind of get our arms around, like, where exactly does the US military use spectrum? So trying to help them modernize the platforms that they use. New spectrum bands, getting more scale, continuing to grow things like CBRS. I showed you the pipeline of other spectrum bands that we're working on. New and innovative ways of bringing more spectrum to the market. In fact, one of the areas that we're very excited about is creating like an Airbnb platform for spectrum, where literally you could go in and lease spectrum on a very transactional basis through a two-sided marketplace. So we've actually been building a lot of technology around how to create Airbnb for spectrum. Doing things like, beyond dynamic leasing, actually sharing spectrum that maybe an AT&T isn't using in a given geography, and making more efficient use of licensed spectrum in addition to, coordinating federal and non-federal uses. In particular, one area that's very exciting is much higher fidelity sharing through use of measurement data and sensing data, active sensing and like the G node B or E node B, and AI and ML. So throwing out this whole notion of propagation models and actually turning this into a big data problem. And doing a lot of work in that area in terms of how we can do that, in a very computationally efficient way. Big part of 6G, if you all are following that a little bit, is around things like terrestrial and non-terrestrial networks. So how we will share with satellite services, LEO, and GEO satellite networks, as well as terrestrial networks that are using common frequency bands. And then finally, blockchain. Everything that we do is around a transaction over an API. The ability to use blockchain and the concept of a distributed ledger of transactions will create a lot more security, especially for spectrum sharing with very sensitive federal uses. So it's just sort of a very broad kind of perspective on some of the R&D that we're doing on spectrum sharing. Quite a lot to do still. A lot of really interesting problems for us to still solve. Hopefully someday, maybe some of you will be involved in that as well. That would be terrific. And with that, if we have some time remaining, I'm happy to answer any questions or. Thank you.
Thank you for the nice talk. I have a couple of questions. First, in the first few slides, when you talked about the radar systems for the neighbor, for example, and the fact that we could be we find that there is a radar now working in a spectrum we allocated to regular users. So how do you actually distinguish that this signal is a radar signal? From a user that you allocated with the
Yes, so that's where all the signal processing that's in that sensor comes into play. So we know the radar signal has some very unique characteristics to it, especially that there's a repetition to it in terms of how the radar operates physically, because these are scanning radars, not electronically scanned, so they rotate. So there's a period of transmission associated with that. Plus certain features that are built into the waveform that allow them to do more accurate detection of the targets. And we can identify those in the signal processing algorithms and say, okay, we know that's a radar. It's not a 4G or 5G signal. And that's what we do to identify, okay, now we're actually detecting a radar at a certain signal level, even when in the presence of other signals.
And the other thing is, you mentioned the smart campus, for example. I remember like in Blacksburg campus, for example, when there is a game, like there is not enough coverage and they bring like a van or drones for coverage. Do you think like this is the optimal way of doing it, or there is a better way to do it? To provide coverage in terms of big events?
In terms of using things like CBRS? Oh, yeah, absolutely. Believe it or not, we've had a lot of discussions with the athletic department about getting better. If you've ever been to a game at Lane Stadium, the cell service is really pretty challenging. We've actually been talking to them about how they could add that capability to enhance the patron experience and also provide the ability to do like real-time credit card transactions on a private network basis with any of the merchants. So when you go to buy, Hokie gear, you can do the swipe the credit card and they'll do a transaction instantaneously. That's a lot more efficient than trying to rely on a carrier network. So yeah, absolutely. Big venues is a sort of a big, big use case as well. Thank you.
Yeah, so thank you for your wonderful talk. I'm curious to hear your thoughts about international harmonization of spectrum sharing. Maybe even more specifically, we are working with a NATO country on some research, and I want to know where do you think, in terms of spectrum sharing, there's the most opportunity with European countries specifically?
Thank you for that question. That's great point. We are seeing a lot of interest globally around spectrum sharing. I think what's a little unique outside the US versus the US is the footprint that in most other countries that federal uses have on spectrum is a lot less than we have in the US, meaning that this need to sort of share between federal uses like, the Department of Defense and commercial uses, it's not as prevalent in most other countries. What they are very interested in, though, and what we've created with CBRS, and they want to figure out a way to import into their countries, is broadening the ecosystem. How do they make their markets more competitive, bring new service providers in, address some of these private network uses? And the discussions that we've been having with folks like Ofcom in the UK, elsewhere, is around these local area licensing concepts where a software platform could be used to manage very sort of precise and local area licenses that could then create much more uses of a given spectrum band versus offering spectrum and licensing it on a nationwide basis, which is what a lot of the regulators do. So is that helping? I mean, that is where I think we see most of the interest around automation and the cloud platforms.
A particular band? Like 6 gigahertz or maybe
6 gigahertz. Well, 6 gigahertz is going to be a global band for sure. Some cases they're following the exact model that we have in the U.S. We're going to be operating in Canada with 6 gigahertz, for example. Brazil, been very active in talking to Saudi Arabia, CST in Saudi Arabia. Bands for like 5G, 3.8 to 4.2 gigahertz is a big band globally. These local area licenses. We actually did a project with Ofcom around demonstrating how you could do that, sort of automate that licensing process. Thank you for that question.
I have a question online. Please share if you have any materials of how to approach decision makers to free up more spectrum as you go.
Sorry, the first part of the question again?
Please share if you have any materials on how to approach decision makers.
Oh, yes.
To free up more spectrum.
Great, thank you. We've got tons of, I'd be happy to share, but we've got tons of information. It is I will just say it is a long and complicated process. As maybe you heard, Federated's foundation work on the CBRS band probably started back in 2009. 2012, things started to gain momentum. 2015, we started to operationalize the company. 2020 was when we went commercial. So like an 8-year process. It's where the trust building comes in. And for a period of time, I was spending a lot of time like at the FCC or DOD, just kind of one by one, building relationships and building trust. But a lot is, you have to become a trusted partner and provide good technical data. Hopefully that was helpful to the online questions.
I have a couple of questions. First is regarding the ESC nodes. The critics of the CBRS, they say that there is adjacent channel and interference being detected as a radar signal, and that creates like activation of the DPAs. How industry is planning or mitigating that impact?
Yeah, so when we first launched our ESC network, we actually started operating the ESCs even before we were sort of fully certified by the FCC to operate. And when we first turned on the ESC network, I can't tell you how many different scenarios that we ran into of sort of false detection events that we had to, sort of progressively work through and develop signal processing capabilities to eliminate. So an example is one of the sensors that we deployed up in Maine was at a lobster shack. And every time they turned on the generator to boil lobsters, it would spew out all of this, EMI, and cause the noise floor of the sensor just across like DC to daylight to just degrade. And we, we were kind of falsely triggering on that. So things as sort of, mundane or benign as that, we had to find ways to adapt to it. So I'd say we've done a lot of work to advance and perfect the ESC technology. It's still a very important component of CBRS. I would also say though that NTIA and the DoD are thinking about something that they call an informing incumbent capability, where they will sort of securely tell us what spectrum is being occupied where. That's probably still a few years off in terms of development, but I do think that may someday replace or complement what we're doing with the ESC.
One more critics, what they say about the DPA calculations, they are also based on the very old census data.
Yes.
Again, the channel modeling is used irregular. So what has been done?
There's actually been a lot of progress since, again, when I go back to trust building, a lot of the protection criteria, the models that we use in CBRS are very conservative. They were intended to be very conservative because the last thing we wanted was an interference event that would, sort of read badly on the viability of spectrum sharing. So we built a lot of conservatism into the model, and we are now progressively working with the DoD. We have weekly meetings with them where we're starting to push things a little bit further forward. So literally the model that we use for propagation modeling for those DPAs is based on Longley Rice. It's now called the irregular terrain model. Sounds super sophisticated, doesn't it? I mean, it's a series of formulas and some terrain data. It's not very advanced or accurate. We're now getting into use of clutter and other, much more precise modeling capabilities. And actually, some of those have now been implemented. So continuing to advance the capability forward.
One more. The incumbent protection is pretty dynamic in itself, but what about the GA coexistence? How dynamic and what is?
So we do that too. That's an excellent observation. So one of the things that we have to deal with is as commercial uses of the band get more pronounced, more prevalent in a certain geography, we have to not only provide protection to say a Navy radar, but also make sure different users get clean spectrum to operate on. And that's what we call coexistence. Today, we as Federated have implemented some algorithms that we are able to steer different users to the different parts of the available band to address that. That's kind of something that we do, I'd say, sort of order of timescales on a daily basis. We might give each of our users a new channel option or channel assignment based on how the GAA use has changed over the course of the day.
Since the SaaS deployment is multi-vendor deployment, Federated and Google are so like doing this with manual negotiations might lead to biases.
Some of it is, I would say it's semi-automated. It's not fully automated. Some of what we do is we kind of agree of the 150 megahertz, since there's more than one spectrum access system. For example, Google operates one. We kind of decide who gets what portion of the band so that we can make assignments in a way that, we don't have to, email them or call them or, do something like that, and we can automate some of that capability. And we're moving towards greater levels of automation.
Thank you for your talking. And when I saw your topic, I'm very excited because I have to do some research in spectrum sharing.
Great.
I do unlicensed band or licensed band sharing in LTE, Wi-Fi by small cell and device to device. And we also can see the unlicensed band and licensed band sharing in 3GPP standard. However, we discussed this issue almost 10 years but we haven't seen this sharing technology implement for now. So because the sharing must be related to different protocol, so we cannot precisely define the criterion about the balance allocation or this resource allocation.
Right.
So what a simple question, what challenge about space-on sharing in basically implement in different protocol communication?
Yeah, I'd say most of the challenges are not technical. They tend to be more business oriented. So equipment suppliers, who are very sort of active in things like 3GPP, developing 4G, 5G, and so on. They have other technology solutions they want to bring to add capacity, improve performance that maybe in some cases are built around their own IP, their own intellectual property. So that's a little bit of the push and pull that you see sometimes globally around standards development and implementing spectrum sharing in, as like a part of 3GPP. Frankly, my perspective is that'll never happen. I seriously doubt that 3GPP will ever really implement spectrum sharing. I think it'll be more how we see it happen has occurred in the US, where the regulator sort of defines a requirement and a framework around which the band will be used and allocated and shared, and then technology will be developed that enables that, and through some lightweight protocol you're able to communicate with the infrastructure and make that possible. So I see them sort of tending to develop more along parallel paths as opposed to converging with one standard. That makes sense.
Okay, thank you.
Thank you.
You're welcome. That's my son. Thank you very much. I appreciate, very grateful for your time and attention, and hope you found it valuable. Thank you.
Thank you.